Let's continue solving problems from the 27th Philippine Math Olympiad qualifying stage. We are now on part 2, problems 6 to 10. Problem number 6. Mark has 60 unit cubes. He arranges the cubes to form a 3x4x5 rectangular prism and then paints all external faces of the prism red. He removes the cubes with less than 2 painted sides. Finally, he completely submerges the resulting solid in a tub of yellow paint. At least how many square units of paint were applied to the solid? Alright, so let's determine first the number of square units of red paint used. We can do this by calculating the total surface area of the rectangular prism. Using the well-known formula for the total surface area of a rectangular prism, we determine that the surface area is 94 square units. So the amount of red paint used is also 94 square units. Now, after removing the cubes with less than 2 painted sides, we must have this resulting solid. This resulting solid is submerged in a tub of yellow paint. Okay, so the new color of this cube now, or this resulting solid, is yellow. Now, so how do we calculate the number of square units of yellow paint used? Let us break this down into cases. So if you examine closely the resulting solid, some of the cubes have 4 faces being exposed to the yellow paint. Others have 3 faces only being exposed to yellow paint. So let's start with those cubes with 4 exposed faces. So how many of these cubes are there? There are 24 cubes with 4 exposed faces. Where can we find them? If you look at the front part of the resulting solid, there are 6 cubes with 4 exposed faces. This one, so 1, 2, 3, 4, 5, 6. There are also 6 exposed faces at the back, right? So that brings to a total of 12. Now, if you look at the sides of the two sides of the resulting solid, you can also find 6. For example, this one, 1, 2, 3, 4, 5, 6, and in the other side, there are also 6 of them. So this brings to a total of 24 cubes. Now notice that for each of the 24 cubes, since there are 4 exposed faces, 4 square units of yellow paint can be used. So a total of 96 square units of yellow paint can be used for the 24 cubes. Now, how many cubes with 3 exposed faces do we have? There are 8 cubes, and these 8 cubes are the corner cubes. Okay, so there are 8 of them. So in the front there are 4, in the back there are also 4, so that brings to a total of 8 cubes. Now, for each of these 8 cubes, 3 square units of yellow paint can be used. So we have a total of 8 times 3, or 24 square units of yellow paint can be used for the 8 cubes. So now we just have to total or sum up all these 3 numbers to get the total square units of paint used. So the answer here is 94 plus 96 plus 24 equals 214 square units of paint, and that is answer choice D. Problem number 7. There is exactly one positive 3-digit number such that if we swap the first and third digits, it increases by 20%. The second digit of this number is what? Let's start by representing the hundreds, tens, and units digits of the number by H, T, and U respectively. So the number can be represented by the expression 100H plus 10T plus U. Now, if we swap the hundreds and the units digit, we create a new number which is represented by 100U plus 10T plus H. Now, as stated in the problem, the new number is greater by 20%. So if we divide the new number by the original number, the result must be 6 over 5. So we have this equation. Clearing the denominators and then solving for t in terms of h and u, we must have t equals 494u minus 595h all divided by 10. Now, what I'm going to do next is decompose the numerator into 490u minus 590h plus 4u minus 5h. Now, why did I do this? By doing this, we can actually determine easily the possible values of u and h, because if we divide each term of the numerator by 10, we have the equivalent expression in the right hand side, which is 49u minus 59h plus 2/5 times u minus 1/2 times h. So we just have to look at the last two terms here. Take note that the possible digits range from 0 to 9. But if you look at 2 over 5 times u, it's very clear that the only value for u that we must consider must be 5, because it's the only number from 0 to 9 that's divisible by 5. Now, you can easily check that the value that works for the hundredths digit is the number 4. Okay, all other possibilities like 2, 6, and 8 do not work. You can easily verify that one. So by substituting u equals 5 and h equals 4, we should get the value 9. Okay, so all other values of h that you can try will make t a 2-digit number or even a 3-digit number. So the answer here is answer choice D. Problem number 8. For a set S, a subset of Z, write pi of S to be the product of all the elements of S. Compute the indicated sum below, where the sum is taken over all non-empty subsets of the set with elements consisting of the first 24 positive integers. Note that for sets with one element, the product will be the sole element. So if there's only one element, the value of pi of S is equal to that element. Alright, so how do we solve this problem quickly? We can solve this problem quickly by looking for a pattern from small cases. So let's do that. We can start with the set containing only one element, 1. Obviously, the non-empty subset for this is this set with element 1. So what's the pi of S for this subset? Take note there's only one element, so the value of pi of S for this subset is equal to that element. So pi of S is equal to 1. And then getting the reciprocal, the value of the indicated sum must be 1 over 1, which is equal to 1. Now let's consider the set with elements 1 and 2. The non-empty subsets of this set are the set with element 1, the set with element 2, and the set with elements 1 and 2. The value of pi of S for the first non-empty subset must be equal to 1. For the second, pi of S must be equal to 2. And for the third, pi of S must be equal to 1 times 2. Now, getting the reciprocal of these products and then summing up, we must have 1 over 1 plus 1/2 plus 1 over 1 times 2. Simplifying, we get an answer of 2. This is the value of the indicated sum. Now, let's have one more case. Let's consider the set with elements 1, 2, and 3. So there are 7 non-empty subsets for this. Take note, we already know how to get pi of S for each of these non-empty subsets. Now, if we take the reciprocals of the values of the pi of S, we have this expression. If we sum them up, we have this expression. And if we simplify, the result must be 3. Now, what's the emerging pattern here? Now, if we go back to the first case, if there's only one element, the answer or the value of the sum is 1. If the elements are 1 and 2, the value of the indicated sum is 2. If the elements are 1, 2, and 3, the value of the indicated sum is 3. So what's the key observation here? So the key observation is that the value of the indicated sum is equal to the number of elements in the set or the highest element in the set. So if the elements of the set are numbers 1, 2, 3 up to n, the value of the sum is equal to n. Now you can prove this one by induction if you want to explore further, if you want to study this one further, but I will not present it. I'll just leave it as an exercise. So with this observation, we say that the answer to the problem is 2024, since the set that we are considering has elements 1, 2, 3 up to 2024. So the value of the indicated sum is 2024, and so the answer is answer choice C. Problem number 9. For some positive integer k, one of the roots of 2x cubed minus kx squared plus 23x minus 1 is an integer. What is the sum of the other two roots? We can apply here the rational root theorem to determine the potential rational roots of the given polynomial. By this theorem, the potential rational roots are plus minus 1 and plus minus 1/2. But since the problem states that one of the roots is an integer, we just have to test plus minus 1. So either 1 or negative 1 is a root of 2x cubed minus kx squared plus 23x minus 1. Now let's apply the remainder theorem. If we assume that negative 1 is a root of the given polynomial, by the remainder theorem, we have that 2 times the cube of negative 1 minus k times the square of negative 1 plus 23 times negative 1 minus 1 equals 0. Solving for k, we get k equals negative 26. But then k must be a positive integer, so negative 1 is not a root of the given polynomial. Now let's test 1. Again, by the remainder theorem, if we assume that 1 is a root, then 2 times 1 raised to 3 minus k times 1 squared plus 23 times 1 minus 1 is equal to 0. Solving for k, we get k equals 24. So 1 is a root. So far we know that 1 is a root and k is equal to 24. So the given polynomial is 2x cubed minus 24x squared plus 23x minus 1. Now remember that we are asked to find the sum of the other two roots. You may find the other two roots, but it's not necessary because we can just apply the Vieta's formula to make the solution shorter. So by Vieta's formula, if we assume that the other two roots are p and q, 1 plus p plus q must be equal to the negative of negative 24 divided by 2. Simplifying, we have 1 plus p plus q equals 12, and so p plus q must be equal to 11. And so the answer is letter A. Problem number 10. In triangle ABC, let D, E, F be points on BC, CA, and AB respectively, such that DF is parallel to CA and DE is parallel to AB. So we have this figure based on the conditions. Now, AE is equal to 4, BF is equal to 6, and CD is equal to 8. And the sum of DE and CE is equal to 20. Find the area of triangle BFD. Alright, so to make our analysis easier, let's introduce some notations for the measures of the angles. In particular, let's denote the measure of angle A by alpha, the measure of angle B by beta, and the measure of angle C by gamma. Now, since DE is parallel to AB, we have that angle CED is equal to angle CAB. So angle CED must also be alpha. And by similar argument, angle CDE must also be beta. Now, since DF is parallel to CA, we have that angle BDF is equal to angle BCA. So angle BDF must also be gamma. And by similar argument, angle BFD must also be alpha. Alright. Now we see also that quadrilateral DFAE is a parallelogram. So DF must also be equal to 4. So DF must be equal to AE, which is equal to 4. Now let's represent DE by X. And since the sum of DE and CE is 20, we can represent CE by 20 minus X. Alright. Now we see some similar triangles. Triangle BFD and triangle DEC are similar, right? So since they are similar, their corresponding sides are proportional. So we have that BF, this one, divided by DE is equal to DF, this one, divided by CE. Alright. So we have the equation 6 over x equals 4 over 20 minus x. Now solving for x, we must get x equals 12. So DE must be equal to 12 and CE must be equal to 20 minus 12, which is 8. Now we see that triangle DEC is isosceles. And since triangle DEC is similar to triangle BFD must also be isosceles. So BD must be equal to 4. Now we can find the area of triangle BFD. Since the three side lengths are given, we can just use the Heron's formula given by A equals the square root of S times S minus A times S minus B times S minus C, where S is the semi-perimeter and A, B, and C are the side lengths of the triangle. So with side lengths 4, 4, and 6, the semi-perimeter is 7. Now we just have to substitute these values in the formula to get this radical expression. And by simplifying, we get the area of 3 square root of 7. And so the answer is letter C.